Hello everybody, myself Prasad Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In our last discussions of this electric machine to class, so we have covered the different methods of speed control of induction motor. Say starting from pole changing, rotor rheostat control, different method of pole changing by injecting slip frequency power to the rotor circuit, and then slip power recovery scheme, etc. We have discussed. We have discussed multiple say. Stator winding, consequent pole changing method, pole amplitude modulations method, rotor rheostat control by operating two motor in cascade, then injecting an EMF in the rotor circuit, that is camera systems, LBS systems, and also we have talk about the slip power recovery scheme, that is static camera system and static reverse systems, etc. So we have covered all the methods of the speed control of induction motor, and now today we'll discuss braking of three-phase induction motor actually. So the braking is the process of reducing the speed of an induction motor. So by braking we can reduce the speed, and in braking, the motor works as a generator, developing a negative torque which opposes the motion of the motor. So the braking of an induction motor is mainly classified into three types. They are actually regenerative braking, plugging or reverse voltage braking, and dynamic braking. So in all the cases we actually reduce the speed. So brake means it will the speed will be reduced, and the process of braking can be classified into normally three types, basically regenerative braking, plugging or reverse voltage braking, and dynamic braking. Okay, so let us start with dynamic or rheostatic braking. So in rheostatic braking, actually one supply line out of the three, that is R, Y, B, is disconnected from the supply. Either R or Y or B is disconnected. So only two supply is available. So depending upon the condition of this disconnected line, two types of rheostatic braking can be achieved. First one is two-lead connection, and second one is a three-lead connection. So this is actually the schematic diagram of a two-lead connection, and this is about a three-lead connection. What we are finding, what is the basic difference here? In two-lead connections, see here. So the supply is in this method, the disconnected line, there is this one. So it is kept open. So instead of connecting it to the R, so it is kept open. So only supply is given from the Y and B to the stator winding, and this is called a two-lead connection. Basically, two leads are connected. And in three-lead connection, so this open lead is not kept open, so it is connected to the another lead of the supply line. So that means this disconnected line is connected directly to other line of the machine. So that is shown here. Okay, and see all this motor actually basically, see this is the rotor circuit rheostat. Okay, and that means this motor is slip ring type, both the cases. Yeah. So this in both the cases actually what we are finding, the disconnected line high resistance is inserted in the rotor circuit, and with the help of this rheostat. Okay, so high resistance is inserted, and thus this method is effective only for slip ring or wound rotor induction motors, and as one of the motor terminals is not connected to the supply, the motor continues to run as a single phase motor basically. And in this case the breakdown torque, that is maximum torque, decreases to 40% of its original value, and the motor develops no starting torque at all, because it's then work as a single phase motor. And due to high rotor resistance, the net torque produced becomes negative and the braking operation is obtained. So basically we want to control the torque production, even if it is produced also, it should be in the negative direction, so that the speed can be reduced and braking operation is say in function, but braking operation is being created. So as I told you, this is basically of two types, either two lead connection, one supply lines is kept open, and three leads connection, one the open circuit is connected directly to the one of the supply line. So as a result, high resistance is inserted in the rotor circuit by rotor rheostat control. And so this method is applicable only for slip-ring induction motors, and since in this case the motor operates as a single phase motors, and so no torque will be developed, and also the breakdown torque or the maximum torque decreases up to 40% of its original value, and due to high resistance the net torque produced becomes negative, and the braking operation is obtained. Okay. So see, this is the torque speed characteristic, this is the maximum torque, this is the starting torque, this is the motoring region, and this is the braking region. So motoring region is slip 0 to 1, and braking region from slip 1 to 2, this is a negative torque. So here the speed is in the synchronous speed in the negative direction, that slip 2, that is the opposite direction. So as a result braking operation will be possible. So actually in this two lead connection the braking torque is small, while in three lead connection the braking torque is high at high speeds. And but in three lead connection there is possibility of inequality between the contact resistance in connections of the two parallel lines, and this might reduce the braking torque, and even may produce the motoring torque again. So hence, in spite of low braking torque, two lead connections is preferred over three lead connections. And this is the torque slip or torque speed characteristics of the motoring and braking operations as shown here. Okay, so that's all about this dynamic braking process. Okay, dynamic or rheostatic braking. So now we'll discuss about plugging or countercurrent braking. So actually the reversal of direction of rotation of motor is the main principle in plugging of motor. So the reversal of direction of motor rotation is the basic principle or main principle behind the plugging of motor. So in case of an induction motor, it can be quickly stopped by interchanging any two stator leads, and as a result the motor will say rotate in the reverse directions. And so due to this, the direction of rotating a magnetic field gets reversed suddenly, and this produces a torque in the reverse direction, and the motor tries to rotate in the opposite directions. And effectively the brakes are applied to the motors. Thus during the plugging the motor acts like a brake. This method can be applied to both squirrel cage as well as wound rotor induction motor, which is not possible in case of dynamic or rheostatic braking. And one important aspect about plugging is the production of very high heat. This is very important, very high heat in the rotor. Okay, so this is the arrangement. So this is the change of say connection. So R is connected to Y and Y is connected to R. So as a result, motor say reverse rotating magnetic field will produce. So it will be the power to the rotor, and it will rotate in the opposite direction. So the load will supply here. So and both this power will be distributed with the heat in the rotor circuit. So while this plugging is happened, the load keeps on revolving, and rotor absorbs kinetic energy from the revolving load and causing speed to reduce. And the corresponding gross mechanical power (PM) is entirely dissipated as heat in the rotor. Similarly, as a stator is connected to supply, rotor continues to receive power P2 from the stator, which will also get dissipated as heat in the rotors. So as a result, the plugging should not be done frequently, because due to this high heat produced, rotor may attain high temperatures, which can melt the rotor bars and even may overheat the stator as well. So this is actually the plugging and its advantage and disadvantage. One advantage is that the plugging is applicable for both squirrel cage and slip ring induction motor both. Since by interchanging the stator leads, basically rotor is being rotated in the reverse direction. As a result, the mechanical power as well as the stator power both are supplied to the rotor, and as a result, rotor will speed will be reduced, and this total power will be dissipated as a heat to the rotors. And due to this high heat, rotor bars may got melted. So as a result, so this is not advisable to apply this plugging method of braking very frequently, and so that's very important. And this is I told you, this is the schematic diagram or block diagram, you can say, of this plugging methodology. So with this braking methods, that is dynamic or rheostatic braking and plugging, we have discussed. Now we can also discuss DC dynamic braking. So actually DC dynamic braking is useful for quick stopping of an induction motor, and its high inertial loads can be achieved by connecting stator terminals to a DC supply. Any two terminals can be connected to a DC supply, and third terminals may be kept open or may be connected directly to the stator terminals, and so this is called DC dynamic braking. Okay, actually this happens for quick stopping of an induction motor, and its high inertial load can be achieved by connecting stator terminals to a DC supply, and any two stator terminals can be connected to a DC supply, and the third terminals may be kept open or may be connected directly to the other stator terminal, and this is called the DC dynamic braking. So this is shown here. See, two terminals is connected to the DC. Okay, here. So input transformer for rectifications, this is supply. Okay, this is supply, and this is connected here. So if the third terminal is kept open, it is called two-lead connections, and while it is sorted directly with other starter terminals, it is called three-lead connection. That base can be used as to get this DC supply, and this is the figure shows a two-lead connection with a diode base for a DC dynamic braking of an induction motor. When DC is supplied to the stator, stationary poles N, S are produced in the stator, and the number of stationary poles is P, for which the stator winding is wound, and as the rotor is rotating, the rotor cuts the flux produced by the stationary poles, and thus the AC voltage gets induced in the rotor, and this voltage produces an AC current in the rotor. So the motor works as a generator. Once again, I am repeating this DC dynamic braking. Actually, if we want a quick stopping of an induction motor and its high inertia load, and that can be achieved by connecting a stator terminal to a DC supply. Any two stator terminals can be connected to a DC supply, and third terminal may be kept open or may be connected directly to the other stator terminals, and this method is called DC dynamic braking. Basically, we are introducing DC supply for braking, and DC supply is connected to the two status terminals, and the third terminal may be kept open or may be sorted to other status terminals. So this is an arrangement of say DC dynamic braking. See, if third terminal is kept open, it is called a two-lead connection, and while if it is sorted directly with other stator terminals, it is called three-lead connections. A diode bridge is used to get DC supply actually. So this is given to the stator winding, the two terminals, and this figure is showing two-lead connections with a diode bridge for a DC dynamic braking of an induction motor. When DC is supplied to the stator, actually stationary poles N and S are produced in the stator. The number of stationary poles is P, for which the stator winding is wound basically, and as the rotor is rotating, the rotor cuts the flux produced by the stationary poles, and thus the AC voltage gets induced in the rotor, and then in that case the motor works as a generator, and and the I square loss or copper losses are dissipated at the expenditure of the kinetic energy stored in the rotating parts, and thus the dynamic braking is achieved. And when all the kinetic energy is dissipated as heat in the rotor, the induction motor comes to rest. Okay. So this is about DC dynamic braking, and it has a very advantage. The heat produced is less than that in case of plugging. Actually, plugging heat production is more, and energy dissipated in the rotor is not dependent on the magnitude of the DC current. So the braking torque is proportional to the square of the DC current actually, and quick stopping of the motor is possible, and the method can be used for wound rotor or squirrel cage rotor induction motors also. So that's all about DC dynamic braking. Now we'll discuss about regenerative braking. Basically, we know the input power of a three-phase induction motor is given by input power equal to 3 times the phase voltage into phase current and the cos of the angle between the phase voltage and the current. So that is the 3 V phase I phase cos phi. Basically, it is the power factor. So phi is the angle between the stator phase voltage and the phase current, and this phi is less than 90 degree for motoring actions. Now, if the rotor speed is increased greater than the synchronous speed with the help of this external external device, it acts as an induction generator, and it converts the input mechanical energy to electrical energy, which is given back to the supply. So it delivers active power to the three-phase line, and the phi becomes greater than 90 degree. In that case, the power flow reverses, and rotor induced EMF and rotor current also reverse, and so the rotor produces torque in opposite direction to achieve the braking. So as the electrical energy is given back to the lines while braking, so it is called regenerative braking. So an arrangement is shown here. This is the arrangement for regenerative braking. So actually This is the induction motor, which can be run as a generator, where its speed is greater than the synchronous speed. This is the supply line, actually. So this is connected to the stator of the induction motor. So this is the load, actually, petrol engine, so external device. So basically this is active power given back to the line. So the torque characteristics of the motoring and generating action is shown here. This is actually the motoring actions, so where the slip is in between 0 to 1, and this is the generating action where slip is greater than 0, and it is at when speed is double of the synchronous speed, it is slip is -1. So this is a slip speed curve. So advantage is that the generated power can be used for useful purposes, and a disadvantage also there. Disadvantage is for fixed frequency supply, it can be used only for speeds above synchronous speed. And so with this we can say complete our discussion about the braking of induction motor. And before going to the next class, with next topic, say we can have quick recapitulations of the entire discussions of today's class. Actually, we have started our discussion with the braking of three-phase induction motor. And braking is nothing but the purpose of braking is to reduce the speed of the induction motor. And this braking, actually in braking, actually motor works as a generator and developing negative torque which opposes the motion of the motor. And the braking of an induction motor is mainly classified into three types: the regenerative braking, plugging or reverse voltage braking, and dynamic braking. And we have discussed about the dynamic or rheostatic braking, where these are also two types. That is, one is 2-lead connections, and another is the 3-lead connection. In 2-lead connections, one lead of the supply given to the stator is kept open, and in 3-lead connection the open lead may be connected either of one with one of the two connected leads. So with this this is possible to have this dynamic or rheostatic braking with the slip-ring induction motors only, because of the rheostat in the rotor circuit is being connected to insert more rotor resistance, increase the rotor resistance. So actually due to this case, motor run as a single phase motor, and in this case the breakdown torque, that is maximum torque, decreases to 40% of the original value, and sometimes so it is in fact since it is a single phase motor, it cannot develop no starting torque at all, and due to the high rotor resistance, the net torque produced becomes negative and the braking operation is obtained. Okay, and this is clear in the torque speed characteristics. In a 2-lead connection, braking torque is small, and while 3-lead connections the braking torque is high at high speeds. But in 3-lead connections there is a possibility of inequality between the contact resistances in connections of the two parallel lines, and as a result this might reduce the braking torque and may even produce the motoring torque again. And hence in spite of low braking torque, 2-lead connections is preferred over the 3-lead connections. And in plugging or countercurrent braking, the speed reversal of the rotation of the motor is the main principle in plugging. In case of neutral, it can be quickly stopped by interchanging the two stator leads, and due to the change, the rotating magnetic field will be produced in the reverse direction, and this produces a torque in the reverse direction, and the motor tries to rotate in the opposite direction. And effectively, brakes are applied to the motor, and thus during plugging, motor acts as a brake, and in the methods of both squirrel cage as well as wound rotor induction motors it is possible. And so plugging is producing some more heat, because the whatever the heat power supply to from the stator to rotor, and since in the rotor is rotating in the opposite direction, so mechanical power is also supplied to the rotor. So both this power are being dissipated as a heat in the rotor circuit, and as a result there is a chance of getting melted this rotor bars, and so plugging is not used very frequently, so it is not advisable also. And in DC dynamic braking, for quick stopping of induction motor, high inertia load can be achieved by connecting stator terminals to DC supply. Any two terminals can be connected to DC supply, and third terminal may be kept open or may be connected to the stator, other stator terminals, and this is the DC dynamic braking. Here, DC dynamic braking for the two terminals case is shown. The third terminal is kept open, and this direct bridge is used to get DC supply, and this supply the static stationary poles are being produced, for which the stator winding is being meant for wound. As the rotor is rotating, the rotor cuts the flux produced the stationary poles, and thus the AC voltage is induced in the rotor, and the voltage produced in the an AC current in the rotor, and the motor works as a generator, and the ice power losses are dissipated, and the expenditure of the kinetic energy stored in the rotating parts. Thus dynamic braking is as if, and when all the kinetic energy is dissipated as heat in the rotor, the induction motor comes to rest. The advantages of this: the heat produced is less compared to that of the plugging. Energy dissipated in the rotor is not dependent on the magnitude of the DC current, and braking torque is proportional to the square of the DC current, and quick stopping of the motor is possible. And this method can be used for wound rotor or squirrel cage rotor induction motors. So, and lastly, we have discussed about regenerative braking. We know the input power of a three-phase induction motor is given by 3 into phase voltage, phase current, and the power factors. And here the phi is the phase angle between the phase voltage and phase current, and phi is less than 90 degree in case of motoring action. And if the rotor speed is increased greater than the synchronous speed with the help of the external device, okay, it acts as an induction generator, and it converts the input mechanical energy to an electrical energy, which is given back to the supply, okay, and it delivers active power to the three-phase line. So in that case, this phase angle becomes greater than 90 degree, and the power flow reduces, power flow reverses, hence the rotor induced EMF and the rotor current also reverse. And so the rotor produces torque in the opposite directions to achieve say braking. And as the electrical energy is given back to the lines while braking, it is called regenerative braking. And this is an arrangement shown here. This is the induction motor. This is the external device for rotating the rotor. This is stator, and this is the sequence supply, and the power back is after regeneration power is back to the main supply. So this is the torque slip characteristic. This is for motoring actions. This is for generating actions. While in motoring, slip is between 0 to 1, and for motoring it is from 0 to the negative -1. For speed is twice the synchronous speed. So S is less than 0, that is negative. Okay, regenerative braking actions. And advantage is that this generated power can be used for useful purposes. And disadvantage is that for fixed frequency supply, it can be used only for speeds above synchronous speed. So with this, we may conclude our discussion about the breaking of the three-phase induction motor. And hope you have understood it. And if any difficulty, you may contact me. We'll discuss.